Have you ever looked up at the night sky and wondered what secrets lie in the farthest reaches of the cosmos? Out there, billions of light years from Earth, some of the universe's most extraordinary objects are waiting to be discovered: neutron stars. These aren't just any stars, they are the collapsed cores of massive supergiants, packing more mass than our Sun into a sphere no wider than a city. But the ones we're about to explore are even more special. They are the most distant neutron stars ever detected, cosmic lighthouses shining from the edge of known space, and each one has a story that challenges what we thought was possible. Today, we're setting off on a journey to uncover 30 incredible facts about these far-flung wonders, from their mind-bending density to the way they warp space and time itself. These distant neutron stars are more than scientific curiosities, they are keys to understanding the universe's deepest mysteries. We'll explore how something so small can influence galaxies, how they serve as natural laboratories for physics we can't recreate on Earth, and why spotting one so far away feels like finding a message in a bottle from the dawn of time. This isn't just a list of facts, it's an invitation to see the cosmos through new eyes, to stand in awe of forces and scales that humble and inspire. So settle in and open your mind to the extraordinary. Whether you're deeply passionate about space or simply curious about the wonders above us, this adventure is for you. We'll make the complex clear, the distant feel close, and the unbelievable undeniably real. By the end, you won't just know more about neutron stars, you'll feel connected to the vast, beautiful, and mysterious universe in a whole new way. Let's begin. To truly appreciate the incredible nature of the universe's most distant neutron stars, we first need to understand what a neutron star actually is. Picture a star much larger and more massive than our own Sun. After burning for millions of years, it exhausts its nuclear fuel and can no longer support its own immense weight. The result is one of the most violent and spectacular events in the cosmos, a supernova explosion. The star's outer layers are blasted out into space in a brilliant flash of light, often outshining an entire galaxy. But what remains at the heart of that cosmic detonation is the star's collapsed core, an object of almost unimaginable density. This is the birth of a neutron star. In that incredible collapse, the forces at work are so extreme that they fundamentally change the very structure of matter. Protons and electrons are squeezed together with such unbelievable pressure that they merge, forming a super-dense ball composed almost entirely of neutrons. Think of it like this: if you could take all the people on Earth and compress them down, they would fit into a single sugar cube. That's the level of density we're talking about. A single sugar cube-sized amount of neutron star material wouldn't weigh an ounce or a pound. It would weigh billions of pounds, as much as a mountain here on Earth. This creates a gravitational field so intense that if you were to drop a marshmallow from just 1 meter above its surface, it would hit with the force of 1,000 hydrogen bombs. Now, while every neutron star is a marvel of physics, the ones that capture the most attention are those we spot from the farthest reaches of the observable universe. Finding a neutron star in our cosmic backyard is one thing, but detecting 1 billion of light years away is an entirely different challenge. It's like trying to spot a single, specific grain of sand on a beach from thousands of miles away using a telescope. The light we see from these distant objects has been traveling for so long that we are essentially looking back in time, witnessing their story from the early chapters of the universe. This makes them not just distant curiosities, but priceless relics that hold secrets about the conditions and the physics that govern the cosmos in its youth. Detecting these cosmic beacons from billions of light years away is a monumental feat of engineering and ingenuity. We can't just point a backyard telescope at the sky and hope to see one. It requires some of the most advanced technology ever built, tuned to see the universe in ways our eyes never could. Most neutron stars reveal themselves not in the familiar spectrum of visible light, but through high-energy X-rays or rhythmic pulses of radio waves. For X-rays, we rely on space-based observatories like the Chandra X-ray Observatory, which acts as a powerful interstellar eye doctor, giving us a clear prescription to see these high-energy emissions without the blurring effect of Earth's atmosphere. In the radio part of the spectrum, colossal installations like the Very Large Array or the upcoming Square Kilometre Array listen to the cosmos, picking up the precise, clock-like ticks from pulsars, spinning neutron stars that sweep beams of radiation across space like a cosmic lighthouse. The greatest challenge in this hunt is the sheer, mind-numbing distance involved. The light or radio waves that finally reach our detectors have been traveling for eons, becoming incredibly faint and stretched out. It's like trying to hear a whisper from someone standing on the other side of a roaring stadium. To overcome this, astronomers often employ a natural magnifying glass provided by the universe itself, gravitational lensing. This phenomenon occurs when the immense gravity of a massive object, like a galaxy cluster, bends and amplifies the light from an even more distant source behind it. This cosmic lens can magnify the faint signal of a faraway neutron star, bringing it into clear view for our telescopes and allowing us to study details that would otherwise be completely impossible to see. Every detection is a painstaking process of collecting these whispers of energy, filtering out background noise from closer objects and instrumentation itself, and then piecing the data together to confirm we've truly found one of these elusive, distant objects. It's a testament to human curiosity and our relentless drive to explore the furthest limits of the known universe. Now, let's meet the current champion, the record holder for distance. The title for the farthest known neutron star belongs to an object with the rather unassuming name of GRB 2113a. It's located in a galaxy so far away that its light has been journeying toward us for approximately 6.5 billion years. To put that immense span of time into perspective, that means this neutron star announced its own birth to the universe back when our own solar system was little more than a swirling cloud of gas and dust, long before Earth had even begun to form. The signal we detected from this event was a gamma-ray burst, an intense flash of high-energy radiation that is the birth cry of a neutron star, and it represents a message from a truly ancient past. Detecting this specific event was a watershed moment in astronomy. The light from this burst was so incredibly faint by the time it reached us that it required the combined power of multiple space observatories, including the Neil Gehrels Swift Observatory and the Fermi Gamma Ray Space Telescope, working in perfect unison to pinpoint its origin. What these instruments captured wasn't a visible image of the star itself, but the brilliant, fleeting signature of its violent formation. This single data point, this echo of a cataclysm from halfway across the observable universe, provides a crucial snapshot of the conditions in the cosmos billions of years ago. It tells us that even when the universe was significantly younger, the fundamental laws of physics were already in place, orchestrating the life and death of massive stars in exactly the same way they do today. The existence of such a distant object forces us to refine our understanding of cosmic evolution. Finding a neutron star from this epoch suggests that the early universe was already quite proficient at building and then destroying the very first generations of massive stars. These stellar explosions were not just spectacular light shows, they were the primary engines for seeding the universe with heavy elements. The iron in your blood, the calcium in your bones, and the oxygen you breathe were all forged in the hearts of stars and then scattered across space by events just like the one that created GRB 2113a. Each distant neutron star we find is a direct confirmation that this cosmic recycling program was operating efficiently, even in the universe's relative youth, enriching galaxies with the raw materials necessary for future planets and ultimately life itself. Now, when we talk about detecting these distant neutron stars, we often aren't just looking for a steady point of light, we're listening for a rhythm. This brings us to one of the most fascinating roles a neutron star can play, that of a pulsar. While all pulsars are neutron stars, not every neutron star is a pulsar. The difference comes down to perspective and motion. Imagine a neutron star spinning at an incredible rate, sometimes hundreds of times per second. As it rotates, it shoots out powerful beams of radiation from its magnetic poles. If those magnetic poles are misaligned with its rotational axis, which they almost always are, these beams sweep through space like the blazing light from a cosmic lighthouse. And if Earth happens to lie in the path of that sweeping beam, we see a regular, repeating pulse of energy with every rotation. From our vantage point, that neutron star transforms into a pulsar, a celestial metronome keeping near perfect time. This precise, clockwork nature is what makes distant pulsars such invaluable tools for astronomers. When we discover 1 billions of light years away, its rhythmic pulse becomes more than just a curiosity, it's a precision instrument. As those beams travel across the vast interstellar distances on their way to us, they pass through the thin gas and dust that drifts between the stars, known as the interstellar medium. This material isn't a perfect vacuum. It subtly affects the radio waves, causing delays that scientists can measure. By analyzing how the pulse's timing changes at different frequencies, astronomers can map out this invisible material, charting the distribution and density of matter across the colossal voids between galaxies. It's like using the pulsar's signal as a probe to take the temperature and measure the composition of the universe itself. But the utility of these distant lighthouses extends even further into the realm of mind-bending physics. The incredibly stable spin of a millisecond pulsar, one that rotates in mere thousandths of a second, creates a timing signal so precise that it can be used to detect the most elusive ripples in the fabric of spacetime, gravitational waves. Einstein's theory of general relativity predicts that cataclysmic events, like the collision of two supermassive black holes, send waves of gravitational energy propagating through the universe. These waves are incredibly faint and notoriously difficult to detect directly. However, as they pass through space, they minutely stretch and compress the distance between objects. By carefully monitoring the arrival times of pulses from an array of pulsars scattered across the galaxy, a project known as a pulsar timing array, scientists can look for correlated tiny shifts in their rhythms. A consistent, synchronized delay across many pulsars would be the telltale sign of a passing gravitational wave, allowing us to sense these cosmic tremors using the galaxy itself as a gigantic detector. Finding such precise pulsars at extreme distances significantly expands the size and sensitivity of this detector, giving us a clearer ear to the hum of the universe. And if the sheer density of these objects doesn't astound you, their incredible temperatures certainly will. We often think of our own sun as being immensely hot, with a surface temperature of around 5,500 degrees Celsius. Now take that number and multiply it by over 100. The surfaces of newborn neutron stars, even those billions of light years away, routinely reach a staggering 1 million degrees Celsius. In their cores, where pressures are at their most extreme, temperatures might soar to values we can barely comprehend, potentially exceeding 1 trillion degrees in the first seconds after their violent birth. This isn't just heat, it's a manifestation of the raw, unbridled energy released when a star's core collapses, an energy so vast it can be detected across cosmic distances. So how do we possibly measure the temperature of an object so impossibly far away that it appears as little more than a flicker of data? Astronomers have developed incredibly clever techniques, turning the faint light we receive into a detailed cosmic thermometer. The primary tool for this is spectroscopy. When the thermal radiation, the light given off purely because of an object's immense heat, from a distant neutron star finally reaches our telescopes, it isn't just a single color. It's spread out into a spectrum, a band of colors much like a rainbow. By analyzing this spectrum with powerful instruments, scientists can identify the specific intensity of light at different wavelengths. A very hot object doesn't just glow white, it has a unique spectral signature, peaking its output at shorter, bluer wavelengths. By finding where that peak lies in the spectrum of a distant neutron star, researchers can accurately calculate its surface temperature, even from billions of light years away. But the work doesn't stop there. The environment around a neutron star is anything but simple. Many are enshrouded in a thin atmosphere, often composed of hydrogen or carbon, and some are still surrounded by the expanding debris of their own supernova explosion. This material can absorb and re-emit certain wavelengths of light, altering the spectrum we observe. To get a true reading, astronomers create sophisticated thermal emission models on supercomputers. These models are virtual laboratories that account for the star's gravity, the composition of its atmosphere, and the effects of its immense magnetic field. They simulate what the spectrum should look like for a star at a given temperature. Scientists then run countless simulations, tweaking the temperature and other variables until the computer-generated spectrum perfectly matches the one they captured with their telescope. It's a meticulous process of cosmic pattern matching that reveals the true fiery nature of these distant embers. This ability to take the temperature of the universe's most distant stellar remnants provides a critical check on our physical theories. The fact that we observe neutron stars in the early universe glowing at these predictable, phenomenally high temperatures confirms that the same thermodynamic principles governing a hot stove here on Earth were in full effect billions of years ago and billions of light years away. It reinforces the beautiful consistency of the cosmos, showing us that the universe operates by a reliable set of rules, allowing us to understand its most extreme inhabitants from the comfort of our own tiny planet. Yet, even among neutron stars, there exists a class of objects so extreme it defies belief. These are the Magnetars, and they possess the most powerful magnetic fields known to exist in the entire universe. To grasp the sheer scale of this power, consider the magnet on your refrigerator. Now, imagine a magnetic field not just a million or a billion, but a quadrillion times stronger than Earth's own protective magnetic shield. The intensity is so incomprehensibly vast that if a magnetar were located halfway between the Earth and the Moon, about 120,000 miles away, its magnetic field would effortlessly erase the data from every credit card on the entire planet. It is a force of nature so potent it can actually twist the very fabric of reality, warping the atomic structure of matter itself in a process physicists call magnetohydrodynamics. These unimaginably powerful fields are the engine behind some of the most violent events we can witness in the cosmos. The crust of a magnetar, a crystalline shell of iron nuclei harder than steel, is locked in a constant, tortured battle with the magnetic field twisted inside it. This creates immense strain, and occasionally the crust can't take the pressure anymore. It cracks. This event is known as a starquake, and it is a cataclysm on an epic scale. The energy released in a single one of these stellar seizures is enough to shake the entire star to its core, and it often triggers a giant flare, a sudden, massive eruption of X-rays and gamma rays. For a few tenths of a second, a magnetar in the throes of a giant flare can outshine every single star in our Milky Way galaxy combined. The truly astonishing part is that we can detect these eruptions from magnetars located in galaxies billions of light years away. In 2020, observatories around the world picked up an immense burst of energy that swept through our solar system. After tracing its origin, astronomers discovered it came from a magnetar in a galaxy over 11 million light years away. The fact that a flash of energy generated by a cracking crystal crust on a city-sized object could be so powerfully bright that it was easily detected from such an incredible distance speaks volumes about the almost unbelievable forces at play. These distant outbursts act like cosmic flashbulbs, momentarily illuminating the vast distances between galaxies and providing a fleeting, brilliant glimpse into the physics of the most extreme magnetic environments. Each detection is a precious data point, helping us understand how matter behaves under conditions so radical they can never be recreated in any laboratory on Earth. But while the incredible speeds of millisecond pulsars are fascinating in their own right, their true value lies in the profound cosmic questions they help us answer. These hyper-spinning stars serve as the most precise clocks in the entire universe, their rhythmic pulses arriving with a regularity that rivals and often surpasses the best atomic clocks we can build here on Earth. This incredible stability transforms them from mere curiosities into fundamental tools for experimental physics, allowing scientists to conduct grand-scale tests of the universe's basic operating principles. To understand how this works, imagine a pulsar's beam as a steady, metronomic flash. Now, if that pulsar is in orbit around another star, its motion will affect the timing of those flashes from our perspective. As it moves toward us in its orbit, the pulses arrive just a tiny bit sooner. As it moves away, they arrive just a tiny bit later. By meticulously mapping these minuscule timing variations over months and years, astronomers can reconstruct the pulsar's entire orbit with astonishing accuracy. This provides a perfect celestial laboratory for testing Einstein's theory of general relativity. The theory makes very specific predictions about how an orbit should gradually decay over time as the system loses energy by emitting gravitational waves. The measurements made by watching these distant, spinning clocks have consistently confirmed Einstein's predictions with breathtaking precision, providing some of the strongest evidence we have that his description of gravity is correct. The utility of these cosmic timekeepers extends even beyond our own galaxy. When a millisecond pulsar is detected in a distant galaxy, its rapid, stable spin becomes a beacon for measuring the vast expanses of intergalactic space itself. The tenuous material that floats between galaxies, known as the interstellar and intergalactic medium, leaves a subtle fingerprint on the pulsar's signal. It causes a slight delay, a dispersion, that affects different radio frequencies by different amounts. By measuring this dispersion in the signal from a pulsar whose distance we can estimate through other means, astronomers can actually calculate the total amount of invisible matter its signal has traveled through. It's like using the pulse as a probe to weigh the nothingness between the stars, giving us a method to map the distribution of this diffuse, dark material across the universe. Each distant millisecond pulsar we find adds another data point, helping us create a richer, more three-dimensional map of the cosmos's hidden structure. But finding a neutron star is only half the story. To truly understand its life, we often have to look at the spectacular aftermath of its birth, which brings us to the glowing, expanding clouds known as supernova remnants. When a massive star explodes, it doesn't just leave behind a dense core. It violently hurls its own outer layers outward at a significant fraction of the speed of light. This ejected material, superheated to millions of degrees, plows through the surrounding interstellar gas, sweeping it up and creating a massive, intricate shell of glowing shock waves. For tens of thousands of years, this remnant continues to expand, a beautiful and chaotic cosmic fossil that tells the story of the star's final moments. And often, sitting right at the heart of this immense structure, is the newborn neutron star itself, the engine that powers the entire spectacle. When we are fortunate enough to spot one of these pairings in a distant galaxy, it provides an unparalleled opportunity for cosmic archaeology. The remnant acts as a time capsule, preserving the composition and velocity of the material blasted out from the star. By analyzing the light from this glowing shell with spectroscopes, astronomers can perform a kind of chemical autopsy, determining exactly which elements were forged inside the star and then scattered by the explosion. We find oxygen, neon, silicon, and iron all present in specific abundances, each element telling us about the nuclear fusion processes that occurred at different layers within the star during its life. This is the process of nucleosynthesis in action, and observing it in galaxies billions of light years away confirms that the same alchemy that built our solar system was already at work in the early universe. The dynamics between the neutron star and its surrounding remnant are especially revealing. The intense particle wind and radiation pouring from the energetic pulsar can inflate a bubble within the larger remnant, creating intricate structures that push against the expanding shell of supernova debris. By studying the shape and evolution of these distant remnants, scientists can indirectly measure the power output and even the age of the central neutron star. It's a complex feedback loop where the remnant reveals the history of the explosion, and the neutron star dictates the future evolution of the remnant itself. Finding such a complete system at a colossal distance allows us to test our models of stellar death against a much wider variety of conditions, showing us how the mechanics of a supernova can vary depending on the mass of the original star and the environment it exploded in. Perhaps most profoundly, each distant neutron star nestled within its remnant is a direct observation of the universe's recycling program operating in the distant past. These cosmic events are the primary foundries for many of the heavy elements essential for life. Every time we confirm one of these pairs in an early galaxy, we are seeing the delivery of enriched material, the future building blocks of planets and perhaps even life, into a young galaxy that was previously dominated only by the pristine hydrogen and helium from the Big Bang. They are not just tombs marking the death of a star, they are nurseries seeding their galaxies with the chemical diversity necessary for the complex universe we see today. While a lone neutron star is a fascinating object, many of these distant cosmic powerhouses are not alone in the void. In fact, a significant number are locked in a gravitational dance with a companion star, forming what astronomers call a binary system. This partnership transforms the neutron star from a solitary beacon into a dynamic and often violent engine. The immense gravity of the neutron star relentlessly pulls material, primarily hydrogen and helium gas, away from its orbiting partner. This stolen matter doesn't fall directly onto the surface. Instead, it spirals inward, forming a superheated, swirling disk of plasma called an accretion disk. As the material in this disk gets compressed and heated to temperatures of millions of degrees, it begins to glow intensely, emitting a tremendous amount of energy, primarily in the form of X-rays. It is this brilliant, high-energy signature that often makes these distant binary systems visible to our telescopes across the vast intergalactic distances. The transfer of matter onto the neutron star's surface doesn't happen calmly or steadily. It can lead to some of the most spectacular and energetic eruptions in the universe. One such event is known as an X-ray burst. Here's how it works. As hydrogen-rich material accumulates on the surface, the incredible pressure and heat from below eventually trigger runaway nuclear fusion. In a breathtakingly short flash, often lasting only from a few seconds to a minute, the entire amassed layer of fuel ignites in a titanic thermonuclear explosion. For that brief moment, the neutron star can become one of the brightest X-ray sources in the entire observable universe, outshining whole galaxies. Spotting one of these bursts from billions of light years away is a stunning feat. It allows astronomers to study the physics of extreme nucleosynthesis in real time, observing how hydrogen is fused into heavier elements like helium, carbon, and oxygen under conditions far more extreme than those in the core of any ordinary star. But the drama doesn't end at the surface. Some of the infalling material, coupled with the neutron star's powerful magnetic fields and rapid rotation, can be funneled away from the poles and launched back out into space at nearly the speed of light. These are astrophysical jets, narrow beams of particles and radiation that can stretch for light years across the cosmos. These jets act like monstrous particle accelerators, far more powerful than anything we could ever build on Earth. When one of these jets is pointed almost directly at Earth, we classify the system as a special kind of object called a microquasar. The term micro is only relative to the jets from supermassive black holes. There is nothing small about the energy involved. The processes within these jets are so energetic that they can produce not just X-rays, but even higher energy gamma rays. Observing these binary systems in distant galaxies provides a unique window into the behavior of matter under the most extreme gravitational influence imaginable. The rate at which matter is accreted, the frequency of X-ray bursts, and the power of the jets all give us critical data. We can measure the mass of the neutron star more accurately, understand the strength and configuration of its magnetic field, and test theories about how material behaves in such a distorted environment. Each distant X-ray binary we discover adds another piece to the puzzle, showing us that these complex and violent stellar relationships were already taking place in the early universe, influencing the evolution of young galaxies by injecting them with enormous amounts of energy and newly forged heavy elements. This journey into the cosmos takes an even more dramatic turn when we consider that these distant neutron stars don't always live solitary lives. Sometimes their fate is to find another and merge in one of the most energetic events since the Big Bang. The landmark proof of this incredible phenomenon came in August 2017, when observatories around the world detected an event that would revolutionize astronomy, GW 170817. For the first time, we didn't just see or hear the universe, we felt it. Gravitational wave detectors LIGO and Virgo sensed the unmistakable ripples in space-time caused by two neutron stars spiraling toward each other in a distant galaxy, about 130 million light-years away. But this was just the beginning. Within 2 seconds of that gravitational signal, a fleet of space telescopes detected a corresponding flash of gamma rays, and then observatories across the globe swiveled to watch as the location erupted into a brilliant, evolving glow across the entire electromagnetic spectrum. This was multi-messenger astronomy born in a single, glorious moment, allowing us to study a single cosmic catastrophe through sound, light, and matter. The aftermath of this collision was a cosmic cauldron of creation. As the two ultra-dense cores smashed together, they blasted a significant portion of their material out into space in immense hot clouds. Within these expanding clouds, conditions were more extreme than in the heart of any star, allowing for a rapid process of nuclear fusion known as rapid neutron capture, or the R process. This is the mechanism long theorized to be the primary source of the universe's heaviest elements. As the material from GW 170817 cooled, its light told a clear chemical story. Spectroscopic analysis revealed the unmistakable signatures of newly forged elements, including enormous quantities of gold, platinum, and other precious metals. The calculations were staggering. The single merger likely produced an amount of gold many times the mass of our entire planet. It was a definitive confirmation that the jewelry we wear and the uranium used in nuclear reactors are not born in the quiet hearts of stars, but in the violent, cataclysmic collisions of dead ones. When we extrapolate this discovery to the most distant neutron stars we can detect, the implications for cosmology are profound. Every time we observe the faint, telltale signs of a neutron star merger billions of light-years away, we are witnessing the primary engine for enriching the early universe with the building blocks of complexity. These distant mergers, occurring when the cosmos was just a fraction of its current age, were seeding pristine young galaxies with the heavy elements necessary to form rocky planets and potentially the chemistry for life. By counting these events and measuring their rates across cosmic history, astronomers can begin to construct a timeline of how our universe evolved from a simple soup of hydrogen and helium into the chemically rich and diverse place it is today. Each distant merger is a data point in the grand story of our own cosmic origins, explaining how the atoms that make up our bodies were once forged in these incredible explosions scattered across space and time. We've talked about the immense density of neutron stars, but what exactly is going on inside them? This is one of the greatest unsolved mysteries in modern physics. We know a neutron star's interior is unimaginably dense, but its exact composition remains hidden from us, sealed away by gravity and conditions so extreme they defy direct observation. To understand why this is such a puzzle, we need to peel back the layers. The outer crust is a familiar, if bizarre, place, a crystalline lattice of atomic nuclei, mostly iron, so tightly packed that it's harder than any diamond. But as we journey inward, the pressure climbs to such insane levels that even those atomic nuclei can't hold their structure. They shatter, and their protons and electrons are forced to merge, creating a vast inner ocean of pure, superfluid neutrons. This neutron superfluid can flow without any friction whatsoever, a property that might explain the sudden speed-ups or glitches we observe in some pulsars. Yet the true heart of the mystery lies even deeper in the very core. Here, the pressure may be so unimaginably great that it overwhelms the fundamental forces that usually keep neutrons separate entities. Physicists theorize that the neutrons themselves might break down into their constituent parts, quarks and gluons. This would create a state of matter not seen since the first microsecond after the Big Bang, a quark-gluon plasma. In this exotic soup, quarks wouldn't be confined within individual protons or neutrons anymore. They'd be free to move around. We might even find strange matter, a form of material made up of strange quarks, which could be more stable than any other matter in the universe. If this exists inside neutron star cores, it would mean these distant objects are actually a new form of stable matter, unlike anything we've ever encountered. So how do we possibly study something we can never see or recreate? This is where the universe's most distant neutron stars become our most valuable laboratories. We can't go there, and we can't build a pressure chamber that powerful on Earth. Instead, we use the stars themselves as our experimental data. The key is something called the equation of state. In simple terms, this is a theoretical model, a physics recipe that describes how matter behaves and responds to different pressures and densities. Different equations of state predict different outcomes. One model might predict that at a certain mass, a neutron star will have a large radius with a soft, compressible interior. Another might predict a very small, incredibly rigid star. There isn't just one theory, there are dozens of competing models, and we need observations to tell us which one is right. Every distant neutron star we detect, especially those with accurately measured masses and radii, acts as a crucial constraint on these models. It's a cosmic reality check. For instance, if we find a neutron star with a tremendously high mass, and we have, with some record holders weighing over 2 times the mass of our Sun, that immediately rules out all the softer equations of state. A soft, squishy interior simply couldn't support that much weight without collapsing immediately into a black hole. The very existence of such massive neutron stars tells us that the matter in their cores must be incredibly stiff, able to resist gravitational collapse with phenomenal pressure. Conversely, if we can measure the radius of a neutron star and find it to be relatively large, that might favor models where the interior is softer and more malleable. The light, or more accurately, the X-rays we receive from these distant objects, carry subtle clues about their size and temperature. By carefully analyzing this emission, astronomers can make educated estimates of a star's radius. When we combine these radius measurements with precise mass measurements from neutron stars in binary systems, we start to paint a picture. We can plot each star on a mass-radius diagram. The correct equation of state must be a curve that passes through all of these data points. Every new discovery, particularly from a galaxy far, far away, adds another dot to this graph. With enough dots, the incorrect models are slowly eliminated, and the true nature of ultra-dense matter begins to reveal itself. It's a slow, meticulous process of cosmic elimination, and each distant neutron star brings us one step closer to solving one of physics' most profound mysteries. And when we push our observations to the very edge of the observable universe, to the most distant and isolated neutron stars, their value as dark matter detectors becomes even more profound. In the crowded environments of modern galaxies like our own, a neutron star's behavior can be influenced by a whole host of factors: accretion from a binary companion, collisions with asteroids, or immersion in dense gas clouds. But a neutron star that formed in the early universe and has been drifting alone in the void of intergalactic space for billions of years presents a uniquely pristine laboratory. With no other celestial objects nearby to complicate the observations, any anomalous heating or a sudden, unexpected glitch in its spin could stand out with much greater clarity. These ancient, solitary sentinels offer a cleaner signal, a clearer window into any potential interaction with the mysterious dark matter that permeates the cosmos. By studying them, we aren't just looking at stars, we are using the universe's most extreme objects to probe its deepest and most elusive secret. This extraordinary precision in timing doesn't just map the space between stars, it provides one of the most independent and elegant methods for measuring one of the most fundamental numbers in all of cosmology, the Hubble constant. This value, represented as h0, is the rate at which the universe is expanding at the current time. Think of it as the speedometer for the cosmos itself. For decades, astronomers have been trying to pin down its exact value with extreme accuracy, but a curious problem has emerged. Two of the most trusted methods for measuring it have been yielding stubbornly different results, creating a significant tension in cosmology. One method uses the cosmic microwave background, the faint afterglow of the Big Bang, to predict what the expansion rate should be. The other method uses a distance ladder, built with pulsating stars called Cepheids and cataclysmic supernova, to measure the expansion rate directly in our local universe. These two methods, both incredibly robust, disagree by a few percentage points. This isn't just a small error bar. It could be a hint that there's a fundamental gap in our understanding of physics, perhaps pointing to new, unknown particles or forces at work in the cosmos. This is where distant neutron stars, specifically those in binary systems, enter the picture as a powerful, independent arbiter. The technique is brilliantly clever and relies entirely on the clockwork nature of pulsars. When a pulsar orbits another star, the precise timing of its pulses allows astronomers to map its orbit in three-dimensional space with incredible accuracy. We know its orbital period, its tilt, and its shape, but there's one thing the pulsar timing alone cannot tell us: the actual physical size of that orbit in light years. It gives us a perfect model, but not the scale. To get that final, crucial piece, scientists look for a subtle effect predicted by Einstein's general relativity, the Shapiro time delay. As the pulsar's signal moves through the gravitational well of its companion star on its way to us, it experiences a tiny, measurable delay. The depth of this delay directly reveals the mass of the companion star. Once you know the mass of the objects in the system, the laws of orbital mechanics unlock the true physical scale of the entire binary system. Now we have a complete picture, a known physical size for the system and a known velocity from the orbital dynamics. But to connect this to the Hubble constant, we need one more thing: the system's relative velocity due to the expansion of the universe, its Hubble flow. This is where the light itself becomes the key. By the time the pulsar's radio waves reach us, their wavelengths have been stretched or redshifted by the expansion of space itself. The amount of this redshift tells us the system's recession velocity. By comparing this cosmological velocity to the independently measured distance to the system, we can calculate the Hubble constant directly. It's a beautifully direct method. Velocity divided by distance equals h0. Using collections of these precise millisecond pulsar systems, like the brilliant work done with the Mir Telescope in South Africa, astronomers are providing a third, completely independent value for the Hubble constant. This new data is crucial because it helps determine which of the two conflicting methods might be experiencing an unseen systematic error, or if the tension is real and we are truly on the verge of discovering new physics. Each distant neutron star acting as a cosmic clock brings us closer to resolving one of the biggest mysteries in modern astronomy. Peeling back the layers of a neutron star brings us to its shimmering outer envelope, its atmosphere. While the interior is a fantastically dense sea of neutrons, the very outer surface is a different world entirely, an incredibly thin shroud of gas, often no more than a few centimeters thick. Yet this delicate layer is our primary window into understanding these distant objects. It's through the unique fingerprint of light emitted by this atmosphere that we can decipher a neutron star's composition, temperature, and even the crushing strength of its gravity. The composition of this atmosphere isn't always the same. Some neutron stars have atmospheres of almost pure hydrogen, while others, particularly older ones that have undergone periods of intense accretion, may have their hydrogen burned away, leaving an atmosphere dominated by heavier elements like carbon or even oxygen. This difference is crucial as the atomic elements present directly control what the star's light looks like to our telescopes. The process of unlocking these secrets is called spectroscopy, and performing it on a neutron star billions of light years away is a true triumph of astronomical ingenuity. We can't see the star's disk, it's far too small and distant. Instead, we collect its photons, the individual particles of light that have traveled across the cosmos for eons. We spread this light out into a spectrum, a band of colors that reveals bright emission lines and dark absorption lines at specific wavelengths. Each element in the periodic table has its own unique set of lines, a barcode that identifies its presence. When we analyze the spectrum of a distant neutron star, we are looking for these telltale signatures. A strong absorption line at a specific wavelength might point to hydrogen, while a different set of lines could reveal helium or carbon. This direct detection allows us to perform a kind of remote chemical analysis, determining the composition of an object we can never hope to visit. But the story these spectral lines tell goes far deeper than just a list of ingredients. The immense gravitational pull on a neutron star's surface, billions of times stronger than Earth's, has a profound effect on the light trying to escape. This gravity is so powerful that it literally stretches the wavelengths of the photons, causing a significant gravitational redshift. This means that the spectral lines we observe are not exactly where they should be for a given element on Earth. They are systematically shifted toward longer, redder wavelengths. The amount of this shift is not random. It is directly proportional to the star's mass divided by its radius. By precisely measuring how far a known spectral line has been redshifted, astronomers can actually calculate the ratio of the star's mass to its radius. This gives us a critical constraint for understanding the star's internal structure and the nature of the ultra-dense matter within it. Interpreting this data requires building sophisticated computer models that simulate the behavior of light in such an extreme environment. Scientists create virtual atmospheres programming in different chemical compositions, temperatures, and surface gravities. They then calculate what the resulting spectrum should look like when observed from Earth. The process involves running thousands of these simulations, comparing each computer-generated spectrum to the actual data collected by the telescope. The model that provides the closest match reveals the true physical conditions on the star's surface. It's a painstaking process of digital matchmaking that transforms a faint, redshifted smear of light into a detailed dossier on a cosmic giant. Each successful spectral analysis from a distant source is a direct confirmation that the laws of quantum mechanics and general relativity operate with perfect consistency, even under conditions of unimaginable pressure and gravity at the edge of the observable universe. To understand why a star becomes a neutron star and not a black hole, we need to look at one of the most critical numbers in all of astrophysics, the Chandrasekhar limit. This isn't just an arbitrary value, it's a cosmic tipping point, a fundamental threshold that dictates the ultimate fate of a star. Named after the Nobel Prize-winning astrophysicist Subrahmanyan Chandrasekhar, this limit is approximately 1.4 times the mass of our Sun. It represents the maximum mass that can be supported against its own gravity by a specific quantum mechanical force known as electron degeneracy pressure. In simpler terms, it's the absolute weight limit for a certain type of stellar corpse called a white dwarf. But how does this relate to the neutron stars we see from billions of light-years away? The journey begins when a massive star runs out of fuel. Its core, now primarily iron, can no longer generate the outward pressure needed to fight the star's immense gravity. The core collapses catastrophically. If the mass of that collapsing core is below the Chandrasekhar limit, it can stabilize as a white dwarf. However, if the core's mass is above that 1.4 solar mass threshold, the collapse doesn't stop there. The force of gravity is so overwhelming that it crushes the core even further, squeezing protons and electrons together to form neutrons. This is the moment of creation for a neutron star, supported not by electron degeneracy pressure, but by an even stronger, more exotic force, neutron degeneracy pressure. This means every single neutron star we observe, no matter how distant, began its life because its progenitor star's core crossed that fundamental Chandrasekhar boundary. When we detect a neutron star in a far-off galaxy, its very existence is a direct confirmation of this physical process occurring in the early universe. But these distant objects do more than just confirm the theory. They allow us to rigorously test it under different cosmic conditions. By studying the light from the supernova explosions that create them and analyzing the properties of the neutron stars themselves, astronomers can essentially weigh the cores of those long-dead progenitor stars. Every time we confirm a neutron star with a mass very close to that 1.4 solar mass limit, it reinforces the astounding accuracy of Chandrasekhar's calculations. Conversely, finding neutron stars that are significantly more massive, and we have found them weighing over 2 solar masses, tells us that additional physics must be at play, such as incredibly rapid rotation or exotic states of matter in the core providing extra support against collapse. This is where distant observations become utterly invaluable. The early universe was a different place. It was hotter, denser, and populated by the first few generations of stars, which were often behemoths made almost entirely of hydrogen and helium. Did these primordial stars, lacking the heavier elements that pepper modern stars, follow the same rules? Did their cores also respect the Chandrasekhar limit? Finding a neutron star from this epoch and accurately measuring its mass provides a definitive yes. It demonstrates that this fundamental law of physics was already in effect, governing stellar death and the creation of neutron stars even when the cosmos was in its infancy. Each distant detection acts as a time-stamped data point, proving the universal and timeless nature of the principles that shape our universe. This relentless dance of creation and destruction, these violent mergers of distant neutron stars, are the very forges where the universe's most precious elements are born. We call the brilliant flash of light from such an event a kilonova, and it is a sight to behold. The name itself tells you about its scale, kilo for 1,000, as these events can be about 1,000 times brighter than a classic nova eruption. But the true magic isn't just in the light show, it's in the alchemy happening within. As two neutron stars spiral together and finally collide, the resulting maelstrom is a crucible of almost unimaginable extremes. The intense neutron flux within the ejected material is so high that atomic nuclei are bombarded, growing heavier and heavier in a frantic process known as rapid neutron capture, or the R process. This is how nature builds the heaviest elements on the periodic table, elements that cannot be forged in the quiet furnace of an ordinary star. In that expanding cloud of stellar debris, atoms of gold, platinum, uranium, and other rare earth elements are created in staggering quantities. Scientists estimate that a single neutron star merger can produce an amount of gold and platinum many times the mass of our entire planet. To put that in perspective, consider the wedding ring on your finger or the electronics in your phone. The gold and other heavy metals within them were almost certainly not made in a supernova, as was once thought. They were most likely born in the violent, cataclysmic collision of two neutron stars that occurred billions of years ago in a galaxy far, far away. That material was then scattered into the cosmos, eventually finding its way into the cloud of gas and dust that would one day coalesce to form our solar system and our planet. We are literally walking stardust, but the most precious parts of us are kilonova dust. When we are fortunate enough to detect the light from one of these kilonovae in a distant galaxy, we are given a front row seat to this cosmic enrichment process in action. The light from the event doesn't just tell us that a merger happened, it carries a specific chemical signature. Over days and weeks, as the kilonova cloud expands and cools, astronomers train their spectroscopes on it. The light is spread out into a rainbow, and within that spectrum, they can identify the unique fingerprints of these heavy elements. They can see the specific absorption lines caused by atoms of gold, platinum, and other R-process elements catching the light. It's a direct, observational confirmation of the theory, allowing us to watch the periodic table being built in real time. The distance of these events is what makes them so profoundly informative for our understanding of cosmic history. Every time we detect a kilonova from a galaxy billions of light years away, we are effectively looking back in time. We are witnessing the chemical enrichment of the universe during its younger, more formative years. This allows astronomers to piece together a timeline, to understand when the first neutron star mergers began to seed the early galaxies with these crucial heavy elements. Before these events, the universe would have been a relatively simple place, composed largely of just hydrogen and helium with a sprinkling of lighter elements from regular supernova. It was the kilonovae that provided the rich diversity of heavier atoms necessary for the formation of rocky planets like Earth, and for the complex chemistry that is the foundation of life itself. By counting these distant flashes and analyzing their light, we are reading the story of our own cosmic origins, written in the element-forging fire of the most powerful collisions in the universe. But what if even a neutron star's incredible density isn't the final form of matter? This brings us to one of the most intriguing hypothetical possibilities in all of astrophysics, the quark star. We've described how the immense pressure inside a neutron star's core might crush neutrons themselves, breaking them apart into their most fundamental building blocks, quarks and gluons. A quark star would be the predicted result of this process, an object where matter has transitioned into a new, stable phase composed of a soup of free-floating quarks, often referred to as strange matter because it could contain a large proportion of strange quarks. In this exotic state, the distinction between individual particles blurs entirely, and the entire core of the star becomes a single, gigantic entity governed by the strong nuclear force in its purest form. The challenge, of course, is that we can't peer directly into the heart of a neutron star to see if it's made of neutrons or quarks. The conditions are so extreme that they exist only in theory and in these distant cosmic objects. This is where observations of the universe's most distant neutron stars become absolutely critical. They serve as our only practical laboratories for testing these radical ideas. The key to identifying a potential quark star lies in its overall size and density. The equations of state for quark matter are fundamentally different from those for neutron matter. Matter in a quark state is theorized to be even denser and more compressible. This means that for a given mass, a quark star would be significantly smaller and more compact than a standard neutron star. Imagine two objects with exactly the same weight, but one is the size of a city and the other is only the size of a large mountain. That's the kind of difference we would be looking for. Detecting this size difference from billions of light years away is a monumental task, but not an impossible one. Astronomers use several clever techniques to estimate a neutron star's radius. One method involves studying the X-ray emissions from a neutron star's hot surface. As the star rotates, hot spots on its surface, like the magnetic poles, move in and out of view, causing a predictable pattern of brightness changes. The specifics of this pattern, known as pulse profile modeling, are exquisitely sensitive to the star's radius. A smaller star would have a different pattern of brightness variation than a larger one. Another method involves analyzing the gravitational redshift of spectral lines from the star's atmosphere, as we discussed earlier, which gives us the mass-to-radius ratio. A star with an unusually small radius for its mass would be a prime candidate for a quark core. Finding such a candidate in a distant galaxy would be a discovery of Nobel Prize-winning significance. It would provide the first direct evidence for a new, stable form of matter that has never been observed on Earth. It would force us to rewrite the textbooks on particle physics and stellar evolution, confirming that the fundamental constituents of all matter can exist in a free state under the most extreme gravitational pressures. Each distant, ultra-dense neutron star we study is a test subject in this grand experiment. Its mere existence pushes the boundaries of what we believe is possible, and its specific properties help us eliminate theoretical models that don't match reality. The hunt for a quark star is a perfect example of how peering into the farthest reaches of the cosmos allows us to answer the most fundamental questions about the nature of reality itself. What truly elevates these distant objects from being mere cosmic curiosities to priceless scientific treasures is their role as the universe's ultimate testing grounds. Here on Earth, our most powerful particle accelerators, like the Large Hadron Collider, can recreate astounding conditions, but they are still fundamentally limited by energy and scale. They can create a quark-gluon plasma, but only for a fleeting fraction of a second in a space smaller than an atom. A neutron star, by its very existence, is a naturally occurring, stable laboratory where the forces that govern the fabric of reality are pushed to their absolute limits every single second. Its entire structure is a perpetual experiment in quantum chromodynamics, the theory that describes the strong nuclear force holding quarks together inside protons and neutrons. The mind-bending density inside its core might be creating exotic states of matter like hyperons or free quark matter, offering us a way to observe how these particles behave under conditions we could never hope to sustain in any human-built machine. This extends beautifully into the realm of gravity and spacetime itself. Einstein's theory of general relativity has passed every test we've thrown at it with remarkable precision, but a neutron star provides a unique environment to probe its most extreme predictions. The theory posits that energy and pressure, not just mass, are sources of gravity. In most objects, this effect is negligible, but inside a neutron star, the pressure is so unimaginably high that it actually contributes significantly to the overall gravitational field, warping spacetime in a more complex way than a simple black hole of the same mass. By carefully measuring the mass and radius of a distant neutron star, often through observations of how its gravity bends the light from a companion star or through its X-ray emissions, we can test these nuanced predictions of general relativity. Each precise measurement is a vote of confidence for Einstein's masterpiece, or potentially a hint that we need to go beyond it. Perhaps one of the most elegant tests involves a pulsar in a binary system with another neutron star. The precise, clock-like ticks of their radio pulses allow astronomers to map their orbits with incredible accuracy. As these incredibly dense objects spiral around each other, they lose energy by emitting gravitational waves, causing their orbits to slowly decay. The rate of this orbital decay, measured over years of patient observation, matches the predictions of general relativity with a precision better than 1%. It's a direct, real-world confirmation of gravitational waves decades before we detected them directly with LIGO. Observing such a system in a distant galaxy doesn't just tell us that the laws of physics work the same everywhere. It demonstrates that the most subtle and complex predictions of our theories hold true across billions of light years and billions of years of cosmic history, providing a profound sense of the universe's beautiful consistency. Considering the sheer age of some neutron stars offers a breathtaking perspective on cosmic history. When we detect one of these objects from a galaxy billions of light years away, we are often looking at a relic from the universe's youth, a stellar fossil that has been cooling for eons. The very oldest neutron stars are thought to have formed within the first few 100 million years after the Big Bang, from the earliest generations of massive stars. These progenitor stars, known as population 3 stars, were behemoths composed almost entirely of hydrogen and helium, devoid of the heavier elements that came from prior stellar generations. Their pure composition meant they lived fast, furious lives, burning through their fuel quickly before ending in spectacular supernova that seeded the cosmos with its first heavy elements and left behind these ancient, dense cores. The key to unlocking the secrets of these primordial neutron stars lies in their temperature, or more specifically, their cooling curves. From the moment of its birth in a supernova's fire, a neutron star is phenomenally hot, but it immediately begins a long, slow process of cooling down. The rate at which it loses this heat isn't random. It's a direct reflection of the physical processes happening within its interior. For the first several hundred years, a neutron star cools primarily by emitting neutrinos from its superfluid core, a highly efficient process that causes its temperature to drop rapidly. After about 100,000 years, this neutrino cooling slows, and the star begins to cool more gradually by emitting photons from its surface, the thermal radiation we can detect with our X-ray telescopes. By studying the surface temperature of a very distant, and therefore very old, neutron star, astronomers can essentially trace its cooling curve backward in time. This allows them to estimate its age and, more importantly, to probe the exotic physics in its core. The cooling rate is exquisitely sensitive to the star's internal composition. Does its core contain exotic particles like pions or kaons that enhance neutrino emission and cause it to cool faster? Or is it composed of superfluid neutrons that slow the cooling process? A neutron star that is cooler than our models predict for its estimated age is a powerful clue that our understanding of ultra-dense matter is missing a crucial piece of the puzzle. Finding these ancient, cold neutron stars is incredibly challenging, as they emit most of their faint light in the X-ray spectrum. It requires space observatories with exceptional sensitivity, like the Chandra X-ray Observatory or XMM Newton, to collect enough of their photons for analysis. Each detection is a precious data point on the cosmic cooling chart. These stellar senior citizens, having silently witnessed most of cosmic history, are the ultimate record keeper. Their present-day temperature holds a coded message about the conditions of the early universe and the fundamental properties of matter under the most extreme pressures imaginable, offering a unique window into the dawn of time itself. Some of the most brilliant and baffling signals in the cosmos are known as fast radio bursts, or FRB. These events are exactly what their name implies, incredibly brief bursts of radio waves that last for just a few thousandths of a second, yet in that fleeting instant, they can release more energy than our sun does in an entire day. For years after their discovery, FRBs were one of astronomy's greatest mysteries, with theories for their origin ranging from colliding black holes to, perhaps more imaginatively, signals from advanced extraterrestrial civilizations. The mystery only deepened when we began detecting some of these bursts from sources billions of light years away, meaning the engine powering them had to be unbelievably energetic to be visible across such a vast cosmic distance. The quest to find the source of these powerful flashes took a monumental leap forward in April 2020. A magnetar within our own galaxy, known as SGR 1935 plus 215, erupted in a massive X-ray burst. While this star had been active before, this time something different happened. Radio telescopes around the world, including the Canadian CHIME experiment, were watching, and they detected an extremely bright radio burst emanating from this same magnetar at the exact same time. For the first time ever, we had a direct, unambiguous link between a specific celestial object and a fast radio burst. This confirmed that at least some FRBs are indeed generated by magnetars, those neutron stars with the most intense magnetic fields in the universe. So how does a magnetar create such an immense, focused flash of radio waves? The leading theory points directly to those unimaginably powerful magnetic fields. The field surrounding a magnetar is under such incredible strain that it can actually twist and fracture the star's solid iron crust, triggering a starquake. This sudden snapping and rearranging of the crust releases a colossal amount of energy, shaking the magnetic field lines anchored to it. Think of it like snapping a giant cosmic rubber band that's attached to the star. This violent disturbance sends a wave of energy racing through the magnetosphere, accelerating particles to near light speed. As these particles interact with the twisted magnetic field, they emit a massive, coherent blast of radio waves, a fast radio burst that can be seen across the universe. When we consider that this process is happening on neutron stars in galaxies far beyond our own, the implications are staggering. A magnetar in a distant galaxy undergoing a starquake would appear to us as a non-repeating FRB, a single, brilliant flash from a specific point in the sky. But some FRBs are different. They repeat, sending out multiple bursts from the same location over days or years. This suggests a different, more sustained engine. One compelling model involves a young, highly active magnetar that is still surrounded by the dense, expanding debris cloud of its own supernova. In this scenario, the repeating bursts could be caused by the magnetar's immense flares slamming into this surrounding shell of material, creating a series of powerful shock waves that then generate the radio emission we see. Each time a new flare erupts and hits the cloud, it produces another FRB. The detection of an FRB from a source billions of light years away does more than just point to a distant neutron star. It allows us to use that flash as a brilliant tool for cosmic cartography. As the burst travels across the vast expanses of intergalactic space, it passes through the incredibly diffuse gas and plasma that floats between galaxies. This material, thin as it is, leaves a subtle mark on the radio waves, causing a delay that affects lower frequencies more than higher ones, an effect called dispersion. By precisely measuring this dispersion, astronomers can calculate the total number of electrons the signal has encountered on its journey, which gives them a measure of the total amount of normal matter it has traveled through. This provides a completely independent way to weigh the invisible, gaseous content of the universe, helping to solve the long-standing mystery of where all the predicted ordinary matter is located. Every time a new distant FRB is detected and its host galaxy is identified, it adds a crucial data point to our understanding of cosmic evolution. These brilliant flashes act like lighthouse beacons in the fog of intergalactic space, illuminating the path their light has taken. By studying the properties of the galaxies that host these magnetars, we can learn about the conditions that lead to their formation. Were they found in young, star-forming galaxies, which would be expected to have plenty of massive stars destined to become magnetars? Or do we find them in older, quieter galaxies, suggesting a different formation path? Each flash is a message in a bottle from a specific time and place in the universe, and by collecting enough of them, we are slowly piecing together a map of how these extreme objects are distributed across cosmic history, revealing the life cycles of the most magnetic stars in the cosmos. But to truly grasp the fundamental nature of these distant objects, we need to take precise measurements, and this brings us to one of the most critical relationships in all of astrophysics, the mass-radius relation. Think of it this way: for any given material here on Earth, its density is a fixed property. A balloon filled with helium is large and light, while a lead weight of the same size is incredibly heavy and dense. The same principle applies to neutron stars, but taken to a cosmic extreme. The way mass and radius are related for a neutron star is not arbitrary. It is a direct consequence of the mysterious physics happening in its core. This relationship acts as a unique fingerprint, revealing the true properties of the ultra-dense matter that makes up the star's interior. Measuring these two properties from billions of light-years away is a feat of astronomical ingenuity, and scientists have developed several brilliant methods to do it. For mass, the most reliable technique comes from studying neutron stars that are in binary systems with another star. By meticulously tracking the orbital dance of the two objects, often through the precise clock-like ticks of a pulsar, astronomers can apply the laws of gravity laid out by Newton and Einstein to calculate the mass of the neutron star with stunning accuracy. It's a cosmic scale that uses orbital mechanics to weigh an object we can never hope to visit. Determining the radius is a different challenge entirely, as these city-sized objects are far too small to image directly, even with our most powerful telescopes. Instead, researchers analyze the light itself, specifically the X-rays streaming from the star's incredibly hot surface. One powerful method involves studying a specific type of binary system where the neutron star is pulling material from a companion. As this gas spirals down onto the surface, it gathers at the magnetic poles, creating intensely hot spots. As the star rotates, these hot spots move in and out of view, causing a predictable pattern of brightening and dimming in the X-ray light we receive. The precise characteristics of this flickering pattern are exquisitely sensitive to the star's radius. By building sophisticated computer models and matching them to the observed X-ray pulses, scientists can effectively measure the star's size from across the universe. Another ingenious technique involves analyzing the spectrum of light from the neutron star's atmosphere. The star's immense gravity stretches the wavelengths of escaping light, an effect known as gravitational redshift. The amount of this redshift depends directly on the ratio of the star's mass to its radius. By identifying specific atomic signatures in the spectrum and measuring how much they have been shifted from their normal positions, astronomers can calculate this mass-to-radius ratio. When this data is combined with an independent mass measurement from a binary orbit, it unlocks both values, giving us a complete picture of the star's fundamental properties. Each new measurement, each data point on a mass-radius graph, acts as a crucial constraint for theoretical physicists. They have developed dozens of competing equations of state, which are complex models that predict how matter behaves under such extreme pressures. Some models propose a softer interior where matter is more compressible, leading to a smaller radius for a given mass. Others suggest a stiffer interior that resists compression, resulting in a larger overall size. The existence of a neutron star with a very high mass, for instance, immediately rules out all the softer equations of state. A squishy interior simply couldn't support that much weight without immediately collapsing into a black hole. Therefore, every distant neutron star we detect and measure is like a vote in a grand cosmic election. Its specific mass and radius combination support some theories while eliminating others. As we collect more of these data points from across the cosmos, the incorrect models are slowly winnowed away, and the true nature of matter at its absolute density limit begins to emerge from the shadows of theory. This painstaking process is how we use the universe itself as our laboratory, employing these distant, spinning beacons to answer one of the most profound questions in physics: what happens to matter when there is nowhere left to go? This process of pulling in and blasting out material is one of the most efficient energy extraction systems in the entire cosmos. and it's all governed by the neutron star's incredible spin and magnetic field. The star's rotation acts like a massive flywheel, storing a tremendous amount of rotational energy, while its powerful magnetic fields channel the infalling material into organized, focused beams. It's the interplay between these two forces, gravity providing the fuel and magnetism providing the guidance system, that allows these jets to achieve such mind-boggling velocities. We're talking about flows of plasma that reach 99.9% the speed of light, making them some of the fastest phenomena we can observe in the entire universe. Observing these relativistic outflows from sources billions of light-years away is like watching a natural particle accelerator of a scale we could never hope to build on Earth. The jets themselves are not just simple beams of light. They are complex structures filled with turbulent, magnetized plasma that can generate radiation across the entire electromagnetic spectrum, from radio waves all the way up to high-energy gamma rays. When one of these jets is fortuitously aligned almost directly with our line of sight, the effects of Einstein's special relativity become dramatically visible. The radiation from the jet appears drastically brighter and more energetic than it would from the side, a phenomenon known as Doppler boosting. This allows us to detect these incredible events from the farthest reaches of the cosmos, turning a distant, city-sized object into a brilliant beacon visible across intergalactic space. The value of studying these distant jets extends far beyond simply cataloging cosmic speed records. They provide a unique laboratory for testing fundamental physics in the most extreme environments imaginable. The mechanism that launches and collimates these jets, how they are formed into such narrow, focused beams and accelerated to such fantastic speeds, is a subject of intense research and debate. By analyzing the light from distant jets, astronomers can work backwards to understand the physical conditions at the base of the jet, just above the neutron star's surface. This helps us understand how energy is extracted from the accretion process and the star's rotation, teaching us about the fundamental laws of magnetohydrodynamics under conditions of gravity and magnetic field strength that are simply unreproducible in any lab. Furthermore, these jets play a surprisingly significant role in the ecosystem of their host galaxies, even those in the early universe. The enormous amount of energy they inject into the surrounding interstellar medium can heat gas, prevent new star formation in their immediate vicinity, and even regulate the growth of the central supermassive black hole. By discovering and studying these powerful outflows in distant galaxies, we gain insight into a form of cosmic feedback that was already shaping the evolution of galaxies when the universe was young. Each distant jet we observe is a testament to the fact that even the smallest objects, through their most violent processes, can have an outsized impact on the grandest scales of the cosmos. While a single neutron star might seem like a tiny speck in the vastness of a galaxy, its cumulative impact, especially in the intense environments of the early universe, can be profound. These cosmic powerhouses act as engines of feedback, injecting energy and newly forged elements into their surroundings, which in turn helps to regulate the very evolution of the galaxies they call home. This process begins with the intense radiation that pours from their surfaces. A typical young neutron star emits a fierce wind of high-energy particles and X-rays, creating a bubble of hot, inflated plasma around itself. In a dense stellar nursery within a distant galaxy, this radiation can heat the surrounding gas, making it too energetic to collapse under its own gravity. By effectively shutting down the birth of new stars in their immediate vicinity, a population of neutron stars can help to dictate the pace of a galaxy's star formation, preventing it from burning through its cosmic fuel too quickly. Beyond this radiative heating, the physical momentum carried by a neutron star's particle wind can have even more dramatic effects. As this supersonic wind slams into the slower-moving interstellar gas, it creates powerful shock waves that compress some material while sweeping other gas away entirely. Imagine a garden hose spraying a powerful jet of water into a pile of leaves. Some leaves are pushed clear away while others are compressed into dense clumps. On a galactic scale, this process can both trigger and quench the formation of new stars. It can clear out vast cavities in galactic nebulae while simultaneously causing the edges of those cavities to collapse under the pressure, seeding the next generation of stars in a shell around the now empty space. This complex, self-regulating cycle ensures that star formation isn't a simple one-off event but a prolonged, feedback-driven process. The role of neutron stars in this cosmic ecosystem becomes even more critical when we consider their final act, their spectacular mergers. As we've discussed, the collision of two neutron stars is a primary source of the universe's heaviest elements like gold and platinum. When such an event occurs in a distant galaxy, it doesn't just create these elements, it violently disperses them at incredible speeds throughout the interstellar medium. This enrichment event is a fundamental driver of chemical evolution. A galaxy that was once dominated only by the primordial hydrogen and helium from the Big Bang becomes peppered with these heavier, more complex atoms. This increased metallicity, as astronomers call it, fundamentally changes how future stars and planets will form. Dust grains composed of these heavy elements help gas clouds to cool more efficiently, facilitating the collapse into new stars and the formation of rocky planets around them. In this way, the death of one generation of stars via neutron star mergers directly enables the creation of the next generation of planetary systems capable of supporting life. This feedback mechanism is a stunning example of how the smallest objects can influence the largest scales. A neutron star is a cosmic paradox, a city-sized remnant that can help to shape the destiny of a galaxy 100,000 light-years across. Their combined radiation, winds, and explosive deaths act as a balancing force, a thermostat that helps to regulate the growth and development of their host galaxies over billions of years. By studying the most distant neutron stars, we are witnessing this feedback process in its earliest stages, observing how the first stellar remnants began to impose order on the chaotic, young universe and set it on the path toward the chemically rich and diverse cosmos we inhabit today. But the influence of these distant powerhouses doesn't stop at enriching galaxies with new elements or regulating star formation. Some scientists speculate they may also be the unseen engines behind one of the most enduring mysteries in astrophysics, the origin of ultra-high-energy cosmic rays. These are not your average particles. We're talking about atomic nuclei, often just single protons, that are traveling through space at a significant fraction of the speed of light, carrying energies millions of times greater than anything we can produce in the largest particle accelerators on Earth. They are the universe's most energetic natural projectiles, and for over a century, their source has been a topic of intense debate and investigation. The sheer energy these particles possess is so immense that when one occasionally strikes the upper atmosphere, it creates a massive shower of secondary particles that can be detected over an area the size of a city. The puzzle has always been, what natural process in the cosmos could possibly accelerate a single particle to such an unbelievable speed? The extreme conditions surrounding distant neutron stars, particularly Magnetars and those in powerful binary systems, make them prime suspects in this cosmic whodunit. To accelerate a particle to such phenomenal energies, you need a few key ingredients: an incredibly powerful and organized magnetic field, a region of immense voltage, and a source of raw particles to act as fuel. A magnetar's magnetic field is the strongest known in the universe, and it's wound up like a colossal spring, storing unimaginable amounts of energy. During a starquake, when this magnetic spring suddenly snaps and reconnects, it can generate enormous electric voltages. We're talking about potential differences that are truly cosmic in scale. In this chaotic, energetic environment, any stray proton or atomic nucleus caught in the crossfire would be subjected to these immense forces, effectively surfing on a wave of magnetic energy that can whip it up to velocities approaching the speed of light. In binary systems where a neutron star is accreting material from a companion, another powerful acceleration mechanism emerges, the pulsar wind nebula. As the neutron star's powerful magnetic field and rapid rotation combine, they can generate a relentless, supersonic wind of charged particles that streams out into space. This wind slams into the slower-moving material around the star, creating a termination shock, a boundary where the particles are suddenly decelerated and their energy is focused. This shock front acts as a natural particle accelerator, far more powerful than any human-made collider, and it can theoretically boost particles to the ultra-high energies we observe in cosmic rays. The jets launched from some of these systems could also serve as efficient particle accelerators, funneling and focusing this immense energy into a narrow beam. The challenge, of course, is that cosmic rays are charged particles, and as they travel across interstellar and intergalactic space, they are deflected by the magnetic fields they encounter. This means that by the time one reaches Earth, it's practically impossible to trace its path directly back to its source. It's like trying to find the origin of a leaf blown into your yard after a hurricane. This is where the most distant neutron stars become so crucial. If a source is far enough away, the chances of a cosmic ray traveling in a straight line to us are vanishingly small unless it is of truly incredible energy. Therefore, when we detect an ultra-high-energy cosmic ray, and we can roughly triangulate its general direction of origin, finding a powerful astrophysical object like a distant magnetar or an active galactic nucleus in that same patch of sky is a tantalizing clue. It provides a candidate source, a celestial factory that we know possesses the necessary conditions to manufacture such a powerful projectile. Each time we correlate one of these rare, ultra-high-energy events with the location of a distant neutron star outburst, it strengthens the case for their role as cosmic accelerators. These distant sources allow us to test our models of particle acceleration under the most extreme conditions imaginable. By studying the light from the neutron star, its X-rays and gamma rays, we can estimate the total energy available in the magnetic reconnection event or the jet. We can then check if that energy budget is sufficient to produce the cosmic rays we detect. It's a complex form of cosmic forensics where the particle is the bullet and the neutron star is the potential gun. Unraveling this mystery is about more than just cataloging sources. It's about understanding one of the most energetic and fundamental processes in the universe, a process that might rely on these tiny, hyper-dense remnants of dead stars to fire the most powerful bullets across the vast expanses of intergalactic space. Even the most precise cosmic clocks occasionally experience a startling hiccup, a sudden and unexpected event that astronomers call a glitch. Imagine a pulsar billions of light years away, its radio pulses arriving on Earth with a metronomic regularity that rivals our best atomic clocks. Then, without warning, its rhythm is broken. The star's rotation suddenly speeds up by a tiny but measurable amount, a fraction of a second, before gradually settling back into its normal, slightly faster pace. This is not a sign of a broken clock. It's a rare and precious glimpse into the turbulent and exotic physics churning deep within the neutron star's hidden interior. For scientists, these glitches are like distant telegrams carrying encoded information about states of matter that simply cannot exist anywhere else. The leading explanation for these sudden speed-ups involves two of the most bizarre properties of a neutron star's interior: its superfluid core and its solid crystalline crust. Picture the star's inner core as a swirling ocean of superfluid neutrons. This isn't a normal liquid, it's a quantum mechanical marvel that flows with absolutely zero friction or viscosity. Meanwhile, surrounding this strange ocean is a solid crust of iron nuclei, a lattice harder than any diamond, locked in a rigid embrace. These two components are supposed to spin together, but they are not perfectly coupled. The superfluid is littered with tiny, whirling tornadoes called vortices, which are normally pinned or anchored to the crystalline structures in the inner crust. This pinning forces the superfluid to rotate at the same speed as the solid crust. However, as the pulsar spins down over millennia, losing rotational energy to its powerful magnetic fields and particle winds, its solid crust slows down ever so slightly. But the frictionless superfluid, with its vortices still pinned, resists this slowdown. It wants to keep spinning at its original, faster rate. A tremendous differential builds up between the two, like a powerful spring being wound tighter and tighter. Eventually, the strain becomes too great. The vortices suddenly break free from their pinning sites all at once and surge outward. This catastrophic unpinning transfers a massive amount of angular momentum from the faster spinning superfluid to the slower spinning solid crust, giving the entire star a sudden, observable kick in its rotation, a glitch. An alternative and equally dramatic trigger for a glitch is a starquake. The neutron star's solid crust is under unimaginable stress, strained not only by the differential rotation with the interior, but also by the intense, twisting magnetic fields frozen within it. Occasionally, this strain becomes too much for the crust to bear, and it fractures not in a small way, but in a planet-scale seismic event. When this happens, the star's moment of inertia changes minutely. To conserve angular momentum, just like a figure skater pulling in their arms to spin faster, the star must increase its rotation rate. This sudden, crustal rearrangement results in the same observed speed up, providing a different window into the structural integrity and elasticity of the hardest material in the universe. Detecting and analyzing one of these events from a pulsar in a distant galaxy is a monumental achievement that offers profound insights. The specific signature of a glitch, how large it is, how quickly the star recovers, and how often these events occur, acts as a direct probe into the star's internal conditions. A large, infrequent glitch suggests a different superfluid properties and crustal rigidity than a small, frequent one. By collecting this data from pulsars across the cosmos, astronomers can effectively conduct a census of neutron star interiors. They can begin to answer questions about the nature of neutron superfluid, the strength of the nuclear posture in the inner crust, and the interaction between the superfluid vortices and the magnetic field. Each distant glitch is a crucial data point that helps us refine our models of matter at densities trillions of times greater than anything on Earth, slowly turning the mystery of the neutron star's heart into a comprehensible, if still astounding, physical reality. While our eyes are limited to seeing the universe in a narrow band of visible light, the true nature of distant neutron stars is revealed only when we learn to see the cosmos in its full spectral symphony. Each wavelength of light, from the long, rolling waves of radio to the incredibly energetic spikes of gamma rays, acts like a different instrument in an orchestra, playing a unique part in the story of these dense stellar remnants. Observing a distant neutron star across this entire electromagnetic spectrum is the only way to assemble a complete picture of its physics, its environment, and its violent history. It's a process of cosmic forensics where each type of light provides a different piece of evidence. Let's start with radio waves, the long wavelength workhorses of neutron star astronomy. This is the domain where we first discovered pulsars, and it remains one of the most vital tools. The precise, clock-like ticks of a radio pulsar are unparalleled for timing. By monitoring these rhythms with colossal dishes like the Very Large Array or the Future Square Kilometer Array, astronomers can track the pulsar's spin, measure its slowdown, and detect the wobbles caused by orbiting planets. But radio observations tell us more than just timing. The way these radio waves are polarized, the orientation of their electromagnetic waves, carries the imprint of the neutron star's incredibly strong magnetic field. As the waves travel through the magnetosphere, the field twists their polarization, allowing us to map its structure around the star. Furthermore, when these radio pulses travel through the tenuous gas of interstellar and intergalactic space, they experience dispersion, a smearing effect that lets scientists calculate the total amount of invisible matter the signal has passed through, effectively weighing the void between galaxies. Moving up in energy, we enter the realm of infrared and optical light. While a neutron star itself is too small and hot to emit significantly in these bands, its surroundings often are. For a neutron star still nestled within its supernova remnant, optical telescopes like Hubble can capture stunning images of the glowing, filamentary debris cloud, revealing its structure, composition, and expansion velocity. Infrared observatories like the James Webb Space Telescope are particularly powerful for peering through cosmic dust to study neutron stars that are accreting material from a companion star. The infrared light from the accretion disk and the heated face of the donor star gives us critical data on the temperature and mass of the material being transferred, painting a picture of the binary system's dynamics. But to truly feel the heat of a neutron star, we must look in X-rays. This is where these objects truly shine, revealing their ferocious energy. Space-based observatories like Chandra, XMM Newton, and nicer are our eyes in this high-energy sky. The surface of a neutron star, heated to millions of degrees from its birth or from ongoing accretion, glows brightly in X-rays. By analyzing this thermal emission, we can act as interstellar thermometers, measuring the star's surface temperature. For pulsars, we can see the hotspots at the magnetic poles whip in and out of view, their X-ray pulses allowing us to model the star's size and geometry. In binary systems, the superheated accretion disk itself emits a torrent of X-rays and sudden thermonuclear explosions on the surface. X-ray bursts create brilliant, fleeting flashes that let us watch the physics of nucleosynthesis unfold in real time. X-rays give us our most direct view of the raw power and violent processes happening on and around the neutron star. Finally, at the very top of the energy scale, we have gamma rays. This is the light of the most extreme events in the universe. NASA Fermi Gamma Ray Space Telescope has revolutionized this field, revealing that many pulsars, especially those with the most powerful magnetic fields, are prolific gamma ray emitters. These beams of ultra-high-energy photons are generated in the outer magnetosphere, where particles are accelerated to near light speed, but gamma rays are also the signature of catastrophic violence. The birth cry of a neutron star in a supernova is a long gamma-ray burst. The star quakes on a magnetar unleash giant flares that can, for a fraction of a second, outshine every other gamma-ray source in the sky combined. And the merging of two neutron stars, as witnessed in GW 170817, begins with a short, intense flash of gamma rays, the first electromagnetic signal of the collision. Detecting these events from billions of light-years away requires a constant watch over the entire sky, a task undertaken by dedicated gamma-ray monitors that alert astronomers around the world to these cosmic catastrophes. The real power, however, lies not in observing these wavelengths in isolation, but in combining them. A multi-wavelength campaign on a single distant neutron star is one of astronomy's most coordinated efforts. Radio telescopes precisely measure its spin. Optical and infrared observatories characterize its companion star and local environment. X-ray telescopes probe its scorching surface and accretion processes, and gamma-ray instruments capture its most energetic outbursts. By stitching all this data together, we move from a one-dimensional view to a rich, multi-dimensional understanding. We can connect the energy output in gamma rays to the structure of the magnetic field measured in radio waves. We can correlate an X-ray burst with changes in the optical brightness of the accretion disk. This synergistic approach transforms a faint, distant point of light into a detailed cosmic laboratory, allowing us to test our theories of particle acceleration, dense matter, and gravity under conditions that will forever be impossible to recreate on Earth. And as we stand on the precipice of this new era of discovery, the tools that will carry us forward are nothing short of revolutionary. The next generation of observatories, currently under construction or in the advanced planning stages, are set to turn the faint whispers of today into the clear, detailed signals of tomorrow, fundamentally reshaping our understanding of these distant cosmic powerhouses. Leading this charge is the Square Kilometre Array, or SCAR, a project of such ambition that it redefines the very scale of astronomical observation. Rather than a single dish, the SKA will be a vast network of thousands of radio antennae spread across two continents, South Africa and Australia, working in perfect synchrony to create a collective collecting area of, you guessed it, a square kilometre. This colossal ear on the cosmos will possess a sensitivity so profound it will be able to detect the faint, rhythmic pulses of a pulsar in a galaxy tens of thousands of light years away as easily as we might hear a whisper in a quiet room. It promises to discover every pulsar in our galaxy and even thousands in nearby galaxies, effectively conducting a complete census of these cosmic lighthouses and giving us an unprecedented statistical sample to understand their life cycles. But the revolution isn't confined to the radio spectrum. The James Webb Space Telescope, already dazzling us with its deep field images, offers a powerful complementary view in the infrared. While Webb cannot see the neutron stars themselves, it is an unparalleled instrument for studying their environments and the aftermath of their cataclysms. Imagine a neutron star merger occurring in a galaxy at the very edge of the observable universe. The brilliant kilonova flash would be detectable, but the real treasure lies in the aftermath. Webb's incredible infrared sensitivity allows it to analyze the chemical composition of the expanding debris cloud long after the initial glow has faded. By dissecting the spectrum of this material, Webb can provide a detailed inventory of the heavy elements created in the collision, the gold, platinum, and uranium, allowing us to measure the yield of these cosmic forges across cosmic time and confirm their role as the primary source of the universe's heaviest elements. Looking further to the future, specialized missions are being designed to probe the high-energy universe with sharper eyes than ever before. The European Space Agency's Athena, the Advanced Telescope for High-Energy Astrophysics, is an X-ray observatory set to launch in the next decade. Its mission is to map the hot and energetic universe, and neutron stars are prime targets. Athena will be able to perform detailed spectroscopy on the X-rays coming from the surfaces of distant neutron stars with a precision that is currently unimaginable. This will allow us to measure their masses and radii with unprecedented accuracy, not just for a handful of nearby stars, but for a whole population across the galaxy. This flood of high-quality data will provide the definitive constraints needed to solve the equation of state puzzle, finally revealing the true nature of the matter squashed into their cores. Will it show us the signature of free quarks or perhaps another exotic state of matter? Athena is the telescope that will likely deliver the answer. And we cannot forget the gravitational wave window, which provided our first glimpse of a neutron star merger with GW 170817. The next generation of ground-based detectors, like the Einstein Telescope and Cosmic Explorer, will be so sensitive that they will hear the cosmic hum of neutron star mergers from the very first billion years of the universe. They will detect these events not as rare, singular occurrences, but as a frequent chorus, allowing us to build a statistical understanding of how often these collisions happen throughout cosmic history. This will tell us the rate at which the universe was being seeded with heavy elements, directly linking the evolution of galaxies to the deaths of stars. Together, these observatories across radio, infrared, X-ray, and gravitational waves will weave a multi-messenger tapestry of data so rich and detailed that the distant neutron stars we once struggled to even detect will become open books, their deepest secrets laid bare for us to read. We are not just building bigger telescopes, we are constructing entirely new senses with which to perceive the universe. While the surface of a neutron star is a hellscape of crushing gravity and searing radiation, making it perhaps the most uninhabitable place imaginable in the universe, these extreme objects nonetheless play a fascinating and indirect role in the grand search for life beyond Earth. Their value lies not as potential homes, but as cosmic signposts and natural laboratories that help us define the very conditions necessary for life to arise in the first place. By studying where and how these stellar remnants form and interact with their surroundings, we gain a clearer picture of the galactic environments that are most conducive to nurturing habitable worlds. Think of a neutron star's birthplace. It begins its life in the cataclysmic supernova explosion of a massive, short-lived star. These explosions are titanic events that blast out enormous amounts of life-threatening radiation and powerful shock waves across light years of space. For any potentially habitable planetary system in the relative neighborhood, a supernova represents an existential threat. A nearby blast could strip away a planet's protective atmosphere or bathe its surface in sterilizing gamma radiation. Therefore, one of the first rules in mapping out galactic habitable zones is to avoid these stellar danger zones. The presence of a neutron star or its glowing supernova remnant acts as a cosmic marker, signaling a region of space that has recently experienced such a violent event. This helps astronomers identify sectors of a galaxy where life would have had a difficult time gaining a foothold, effectively drawing a map of places to avoid in the search for living worlds. Conversely, the destructive power of a supernova and its neutron star remnant is paradoxically linked to the creation of life's essential ingredients. We are, all of us, made of stardust, and a significant portion of that dust was forged in these very explosions. The intense heat and pressure of a supernova are responsible for creating many of the elements heavier than iron, such as iodine, which is crucial for human biology, and uranium, which helps keep Earth's core molten and its magnetic field protective. When a neutron star is involved in a merger, as we've seen, it produces a kilonova that seeds the cosmos with gold, platinum, and other rare Earth elements. These elements are scattered into the interstellar medium, eventually becoming incorporated into new generations of stars and planets. So, while you wouldn't want to live next door to a neutron star, you absolutely want your solar system to form in a galaxy that has been enriched by the materials they create. Their existence ensures that future planets will have the rich chemical diversity needed for the complex geology and chemistry that underpins life. This duality makes neutron stars key players in understanding the concept of galactic habitability. A galaxy needs to have had enough generations of stars to be sufficiently enriched with these life-critical elements, but it also cannot be so active with stellar births and deaths that planetary systems are constantly being bombarded by radiation from supernova. The rate at which neutron stars form through supernova and mergers is therefore a critical factor in determining whether a galaxy as a whole can be considered a likely cradle for life. A very active, star-forming galaxy might be too violent, while an old, quiescent galaxy might be too metal-poor. Finding that Goldilocks zone, a galaxy with a balanced history of stellar activity, is a direct result of understanding the life cycles of the massive stars that become neutron stars. Their distribution and population within a galaxy tell us the story of that galaxy's past violence and its potential for fostering life in the future. Ultimately, the study of these incredible objects helps us refine the parameters of our search. They teach us that a habitable world requires more than just being the right distance from its star to have liquid water. It must also exist in a safe neighborhood within its galaxy, one that has been enriched by the products of past stellar explosions but is not so active as to pose a constant threat. Each neutron star we catalog, whether in our own galaxy or in 1 billion of light years away, adds a data point to our understanding of cosmic evolution and the delicate balance between creation and destruction. They are the stark, brilliant markers that help us read the map of the cosmos, guiding us toward the quiet, enriched corners where life might have finally found a peaceful place to emerge and flourish. Beyond the hard data and complex equations, these distant cosmic powerhouses have also ignited our collective imagination, weaving their way from the realm of astrophysics into the very fabric of our culture. The sheer, mind-bending nature of a neutron star, a city-sized object with the mass of a sun, a magnetic field that could erase your credit card from halfway to the moon, feels like it was ripped straight from the pages of the most ambitious science fiction. And in many ways it has been. These incredible objects have become a staple of the genre, serving as spectacular backdrops and plot devices that allow writers and filmmakers to explore the extremes of physics and human endurance. We see this fascination play out in blockbuster films and beloved novels, where neutron stars often represent the ultimate frontier or the most deadly obstacle. A spaceship might need to slingshot around one to achieve impossible speeds, or a crew might venture into a pulsar's radiation-filled environment, facing lethal doses of X-rays and gamma rays in a race against time. While these scenarios take creative liberties, they are grounded in a kernel of scientific truth, and that's what makes them so compelling. They take concepts that might otherwise feel abstract and distant, like intense gravity or particle jets, and translate them into visceral, high-stakes adventures. This storytelling does more than just entertain. It demystifies complex astrophysics, making concepts like time dilation and tidal forces accessible and exciting to a global audience. This cultural footprint extends into video games and other interactive media, where players can virtually navigate these extreme environments. Games might feature missions to mine the unbelievably dense crust of a neutron star for fictional supermaterials, or to outrun the sweeping death beam of a pulsar. Through these interactive experiences, players aren't just hearing about these concepts, they are engaging with them, developing an intuitive, if simplified, understanding of the forces at play. This playful engagement is a powerful gateway, often sparking a deeper curiosity that leads players to seek out documentaries, books, or articles to learn what's real and what's artistic license. It transforms the neutron star from a cold, distant fact into a dynamic character in the story of the universe. Perhaps the most profound impact of this cultural representation is its ability to inspire the next generation of explorers, engineers, and scientists. A child watching a heroic astronaut navigate a pulsar field in a movie might be seeing their future self. That spark of wonder, that moment of asking, could that be real? Is where many scientific journeys begin. These stories make a career in STEM science, technology, engineering, and mathematics feel not just important but thrilling and heroic. They provide a narrative that textbooks alone cannot, connecting the dry rigor of mathematical formulas to the epic, awe-inspiring scale of the cosmos. By seeing these concepts brought to life in popular media, young minds are encouraged to dream big and to see the universe not as a closed book of known facts, but as an endless frontier of mysteries waiting to be solved. In this way, the cultural life of a neutron star completes a beautiful, full-circle journey. It begins with a real, violent astrophysical event billions of light years away, observed by scientists using the most advanced technology on Earth. That discovery then filters into our collective consciousness, inspiring artists and storytellers to interpret it. Their creations, in turn, captivate and inspire new minds who may one day become the scientists who make the next great discovery about these very objects. The neutron star is more than just a subject of study. It is a catalyst, a beacon that draws us all, scientists and dreamers alike, deeper into the magnificent mystery of the cosmos. And yet, for all we have learned, the universe's most distant neutron stars remain shrouded in profound mystery, each answered question giving rise to a dozen more that beckon us further into the unknown. Perhaps the greatest enigma of all lies hidden beneath their impenetrable surfaces, in the very heart of these cosmic giants. Despite our most sophisticated theories and powerful observatories, we still do not know with absolute certainty what exists at the core of a neutron star. Is it a superfluid sea of neutrons, a bizarre state of matter known as nuclear poster, or a soup of free quarks creating the fabled quark star? Each possibility represents a fundamental rewriting of the rules of physics, and the true answer remains locked away by gravity, waiting for a future observation or a theoretical breakthrough to set it free. Equally puzzling are the precise origins of some of the most energetic signals we detect from the depths of space. While we have firmly connected some fast radio bursts to the spectacular starquakes of Magnetars, others continue to defy easy explanation. Why do some of these brilliant flashes from billions of light years away repeat in unpredictable patterns, while others are solitary, one-off events? Could there be multiple engines powering these cosmic explosions, perhaps involving different types of neutron-star interactions or even more exotic physics we have yet to imagine? Every new burst that arrives at our telescopes is a piece of a puzzle we are still assembling, a reminder that our catalogue of cosmic phenomena is far from complete. These lingering questions are not a sign of failure, but a beacon guiding the future of exploration. They are the reason we build ever more sensitive telescopes and develop ever more ambitious space missions. The journey to understand these distant stellar remnants is a continuous cycle of discovery, where each new finding refines our questions and pushes the boundaries of human knowledge a little further. The greatest lesson these neutron stars teach us is humility. They remind us that the universe is vast, strange, and full of wonders that consistently defy our expectations. Our quest to understand them is far from over in many ways. It has only just begun. From their violent birth in supernova explosions to their silent work as cosmic lighthouses billions of light years away, neutron stars are truly the universe's ultimate marvels. We've journeyed through 30 incredible facts, exploring how these city-sized objects pack the mass of a sun, creating densities where a single sugar cube would weigh as much as a mountain. We've seen how their immense gravity warps space-time itself, and how their collision forges the gold in our jewelry and the uranium in our reactors. They serve as natural laboratories, testing the laws of physics under conditions we can never recreate on Earth, from the superfluid vortices in their cores that cause star-quaking glitches to the magnetic fields so powerful they could erase every credit card on Earth from halfway to the moon. These distant sentinels act as cosmic clocks, helping us measure the expansion of the universe and map the invisible matter between galaxies, while their brilliant flares as magnetars illuminate the mysteries of fast radio bursts. They are both creators and destroyers, seeding galaxies with the elements for life while marking regions of cosmic violence, and their study requires a symphony of light from radio waves to gamma rays to piece together their secrets. Yet for all we've learned, the greatest mysteries remain locked within their cores, driving the next generation of telescopes and inspiring us to keep looking deeper. This journey doesn't end here. The cosmos is filled with endless wonders waiting to be uncovered. If you're as captivated by these distant giants as we are, make sure to subscribe and hit the bell so you don't miss our next adventure into the depths of space. We love hearing from you, so let us know in the comments which fact completely rewired your brain. Was it the idea of a starquake, the cosmic gold factory of a kilonova, or the precise clock of a pulsar guiding us through the universe? Share this video with someone who loves to ponder the big questions and never stop looking up. The universe is telling its story, and we're just beginning to learn how to